Alright, let's have a look at Markov chains. So Markov chain is going to be a stochastic process. We're going to have a sequence of possible states, and transitions between these states are going to be given by probabilities. So for example, we might have three states, A, B, and C. Maybe there's a 10% chance of going from A to B and a 90% chance of staying in state A. Then there might be a 100% chance of going from B to C, a 15% chance of staying in C, and then an 85% chance of going from C back to A. Now, given this Markov chain here, we can define what's called a transition matrix, and each element in the matrix is going to tell us the probability of going between a pair of states. So if we look at the top row of this transition matrix here, this gives me the first element, the probability of going from A to A, then the probability of going from A to B, the probability of going from A to C. So we can fill in these numbers from the Markov chain diagram above, and this is what we get. And then what we notice is that because a row in this transition matrix corresponds to the probability of leaving a given state and arriving at a different state, they therefore all add up to 100%, which is just a law of conservation of probability. Basically just saying, once we're in a state, there needs to be 100% probability of going somewhere. Now, like, we don't necessarily have to go to a different state. For example, the diagonal elements of this matrix correspond to staying in a particular state. So there's a 90% chance of staying in state A if we're in state A, 0% chance of staying in B because we have a 100% chance of going from B to C, and there's a 15% chance of going from C to C. So when we give something the term Markov, usually what we mean is that it is memoryless. So in the context of Markov chains, what this means is that the probability of going from one state to another only depends on the state that you're currently in, not on any past states that you were in before that. So given some set of states x and some discrete time steps I, the probability of going to the next state, given that we're in the current state and given that we were in the state before that, and so on and so on, all the way up to the initial state that we were in, is just equal to the probability of going to the following state given the fact that we're in the current state. So what that essentially means is that all of this memory, all of the past states before the one that we're currently in, don't matter. They don't contribute to this probability here. So my PhD thesis was related not necessarily to Markov chains, but I look at these quantum systems which are so-called non-Markovian. And what that means is that we have some open quantum system and it interacts with some bath. And in a Markovian system, this interaction is sort of one way. The system can interact with the bath, and the bath can influence the system, but the bath forgets the state that the system is in. Whereas a non-Markovian system, the bath remembers what state the system is in, and it can sort of remind the system what state it used to be in. And that leads to these interesting dynamics of these open quantum systems. So let's say we're given some Markov chain and we want to find out what's the expected number of time steps we expect it to take to reach some state I, given that we start in some state J. So the answer to that is going to be, well, it's going to depend on what state we start in. If we start in state I, then obviously it's not going to take us any time to reach state I, so the answer is just 0. Whereas if we start in some state that is not equal to I, the answer is 1 plus the sum over all states k times the probability of going from J to k times the expected number of steps that it takes to get to I from k. So k loops over all possible states. This is going to give us a system of linear equations that we need to solve simultaneously. Let's have a look at a quick example. We want to find the expected number of steps to get from state A to state C. So here we're given the diagram of the Markov chain with the states and the transition probabilities. So let's first of all write our transition matrix out. And then here we see a little representation of what probabilities have gone where inside the transition matrix. So here we just run through the steps of the calculation. The sum over k is going to be, sum over k is either state A, B, or C. So these labels represent the different states. So here we have the expected number of steps to reach C from A. Here we have it from B, and here we have it from C, which obviously is equal to 0 because it takes no further time to reach C if we begin in C. So if TC is equal to 0, then we can remove these two terms here, and then we can just input these probabilities, and then we can solve, and we get that the expected number of steps to reach C from A is 7 1/3, and then we can also easily find the expected number of steps to get from from B to C, and that is 5 1/3. So now let's look at an example that might not obviously be a Markov chain problem, which is, imagine that we are stood on the corner of a cube and we can only walk along the edges of the cube, and we want to know how long will it take us, or how many steps will it take us on average to reach the opposite corner of the cube. So here's our corners of the cube. These are some possible paths that we could take from this green corner here to try and get to this purple corner here. So the starting point is 3 steps away from the target. So for example, if we start here, it would take me 1, 2, 3 steps in the best case to reach the target state. And there's a probability of 1/3 of going in the right direction along each one of these steps. So we definitely expect the expected number of steps to reach the target state to be more than 3. So one thing which can help us realize that this problem requires us to use Markov chains is just by relabeling all of the vertices of this cube in terms of how many steps away they are from the target state. And the reason we can do this is because the cube is symmetrical. So for example, let's start off with the obvious one. The target state is 0 steps away from the target state. And then these 3 here are all 1 step away. These 3 are all 2 steps away. And then our initial state is 3 steps away. So now we need to find out the transition probabilities. So in this case, the probability of transitioning from state I to state J is going to be 1/3 times the number of ways that it's possible to go from state I to state J. So for example, the probability of going from a state which is 2 steps away to a state which is 1 step away is 2/3. Let's see why. Well, here is an example of a state which is 2 steps away. Now there are 2 possible paths which can take me to a state which is now only 1 step away from the target. Each one has a probability of 1/3, so therefore the probability is 2/3. And then from the state which is 2 steps away, there's a probability of 1/3 of me going back to a state which is 3 steps away. So therefore the probability of going from 2 to 3 is 1/3. And of course we have that the probability is equal to 0 if we're asking what's the probability of going from a state which is 1 step away to 1 step away. Well, we can see that that's actually not possible. Every state which I can go to from 1 step away is either 2 or 0 steps away from the target. And it's the same for all others. So basically what that means is we have to move either 1 step further or 1 step closer to our target. We can't stay where we are. So now let's redraw this as a Markov chain where each state represents the number of steps we are away from the target state. So there's a 100% probability of going from a state which is 3 steps away to a state which is 2 steps away, one of these 3 possibilities here. Now from a state which is 2 steps away, we have a probability of 2/3 of going to a state which is 1 step away, probability of 1/3 going back to a state which is 3. And the same for 1 step away, we can go to the target state with probability 2/3, or we can go back to the state which is 2 steps away with probability of 1/3. And then of course, once we're in the target state, we're going to stay there. So here's our transition matrix. We can label the rows as being where we're going from, and the columns as being where we're going to. And then we can just fill in the probabilities as so. And then we use our system of linear equations to find the number of steps that we expect to take from each one of these states. Again, we use this sort of boundary condition that the expected number of steps to get from the target state to the target state is going to be 0, and that helps us simplify things down. And from this, we get that the expected number of steps from our initial state, which is over here, to get to our final state, which is here, is going to be 10. So now let's talk about the property called absorption. Now, an absorbing state in a Markov chain is one for which there's no probability of leaving that state. So what it means is that if I'm in that state, the probability of me going back to that state at the next time step is 100%. So if we reach one of these states, we get stuck in it forever, which is why we use the term absorbing. We get absorbed into this state. And we can easily spot absorbing states by just looking at the transition matrix. And if there are any diagonal terms which are equal to 1, then that is an absorbing state. So for example, going back to this example that we saw a few slides ago, we can see that state C is an absorbing state because it is the only term in this case which is 1 along the diagonal. And we can easily see it from the diagram here. The only way that we can, well, we cannot leave state C once we reach it. We just go back to state C with 100% probability. So in this example here, there's only one absorbing state, which is state C, but it's entirely possible to have more than one absorbing state. So for example, we could have a state D here. Maybe there's some probability of reaching it from state A. I would have to change these probabilities to account for that. So let's change this one to, I don't know, 0.4, which would then mean that there's a 10% chance of reaching state D. And then maybe if we reach state D, there's a 100% chance of us staying in state D. So it's entirely possible to have more than one absorbing state in a Markov chain. So with that in mind, let's consider a Markov chain which has multiple absorbing states, which we label A, and then other transient states, which we call S. So here we can see the transient and the absorbing states. Now let's ask the question, what's the probability of being absorbed by a specific one of these absorbing states, given that we start in some specific transient state? And to calculate that, we want to calculate the probability of being absorbed in state AJ, given that we start in state SI. And for this, we'll set up another set of linear equations, which is going to give us the probability of being absorbed in state J, given that we start in state I, sum over all the states of the probability that we get absorbed in state J, given that we start in state K, times the probability of going from I to K. Now, something that can be quite confusing is where does state AJ come into this? And the answer is in this boundary condition. So we set the probability of being absorbed in state AJ as equal to 1 if we start in that state. Whereas if we start in any other absorbing state, the probability of reaching the absorbing state AJ is equal to 0. Why is that true? Well, if you start in another absorbing state, you're not going to leave that state by definition. So therefore, the probability of leaving that absorbing state and then reaching another absorbing state is going to be 0. So let's have a look at this example. We want to know what is the probability of being absorbed by state D if we begin in state B. Now I've labeled the states here, A, B, C, and D. The absorbing states, let's find any terms which are 1 along the diagonal, so that's states A and D. Now we set this state that we begin in, which in this case is B, and then we set our target absorption state by specifically setting AD is equal to 1 and AA is equal to 0. Why is this true? Well, if we begin in D, there's 0 probability of leaving D, so therefore there's 100% probability of staying in D. Whereas if we begin in A, because it's an absorbing state, we cannot leave it, therefore we cannot reach D. So the probability of reaching D, if we begin in A, is equal to 0. Now what's nice here is that it's very easy, therefore, to find out the probability of being absorbed in A instead. All we need to do is swap these two numbers around. So here's our system of equations that we need to solve. We can make this easier because we know the probability AA is equal to 0 and AD is equal to 1. And we can solve this system of equations and we find that the probability of being absorbed in D, given that we start in B, is equal to 40%.